In this session, in this video, we're going to discuss refraction and reflection. It's important to take some notes because this is some important fundamentals of how telescopes work and the important principles that are behind them. The principles behind telescopes deal with a very simple principle called Snell's Law. If we have light that is traveling from, say, air to glass, that light will be reflected and refracted in different ways. For example, in this picture, coming from the left side, we have some light that is shining in. They call that the incident light ray. And where the glass and the air meet, notice it's just a simple straight line. And for our purposes, notice that the perpendicular line that goes through the air and goes through the glass, that is called the normal line. That's a mathematical name for any line that's perpendicular to something else. So in this case, the normal line is perpendicular. And we measure angles here from the perpendicular, from the normal. So notice we have an angle as the incident light ray comes in, the approaching light ray, and we use a Greek letter to indicate that angle. And so the incident light comes in, travels in toward the place where the air and the glass meet. It strikes the glass, and that ray, then that light beam gets reflected. And so we have light coming in, light going out. And notice here that we have this light ray going out has an angle with the normal, and it has a name. Notice it's a Greek letter theta, the same as the other one, and we put a prime above it. That's a prime, an apostrophe, so that the angle coming in, the angle of the incident ray, is equal to the angle of the reflected ray. So the angle of incidence equals the angle of reflection. That's Snell's law. For reflection, angle of incidence is equal to the angle of reflection. Pretty simple, pretty straightforward, something you've experienced yourself. In order to see someone, if you're off-placed in front of a mirror and you want to look at them, you have to be at the same angle they are, because the light ray gets reflected. Angle of incidence equals the angle of reflection. So it's pretty straightforward and pretty simple and pretty easy to use. So in particular, when you have a flat piece of glass and you put some coating on it, some aluminum coating on it, it'll reflect, and you have a typical mirror. When the light ray, however, goes through the glass, something else occurs. And so we have the angle of incidence here designated by this Greek letter theta, theta sub 1. And so as the light ray comes in and hits the glass, it gets bent, or it gets refracted, the term is. Refracted. The angle becomes smaller, so that the refracted ray is smaller than the incident ray. So in this case, the light gets refracted toward the normal. And it turns out that the shorter the wavelength of light, the more it gets refracted. Shorter wavelengths get refracted more. And so that's the effect of what happens in a prism. When light passes through a prism, it gets refracted. Blue gets refracted more than red, and so we get a prism effect, or a spectrum of light that we will use to talk about the properties of stars, because there's a message in starlight. So in this case, the principle of Snell's law with refraction is that that light that gets refracted, it gets refracted toward the normal. So these two angles are not equal. The angle of incidence is greater than the angle of refraction. Here's an example of this actually measured, where someone set up a device that measures these angles. So on this side, we have the light beam coming in. Notice its angle, 0 degrees is at the top. And remember, this angle is measured. There's the vertex of the angle. So we have the light coming in from the left, coming down, striking this. Notice this is some sort of liquid in here, or maybe it could be a piece of glass. Light comes in, it strikes, it enters the other substance, and its angle of refraction is much less than its angle of incidence. So looking at this again, you can see the light ray coming in, strikes the other surface. Can't see the reflection very easily, but in particular, the angle of refraction is much smaller. It's approximately 45 degrees compared to 70 degrees for the incident ray. So here's an example of what happens when refraction occurs. Telescopes use both refraction and reflection. Here is another simpler demonstration of refraction. In this case, light is going from air into water, and notice this pencil appears to be disconnected because refraction bends the rays, and so what we see is different really from what is in this case. The light, it gets refracted, so this pencil does not seem to be a constant straight line as it moves, as the light moves through the water. It appears to be offset a little bit. So this is a common example of refraction, when light goes from a less dense medium, air, into water, which is more dense, gets refracted. Air into glass, air into water. So briefly, these principles applied to the basics of telescopes. There are two types of lenses. In this picture, notice it says it's a converging lens. Sometimes, in many cases, this is called a convex lens. Notice that the edges of the lens are thicker than the middle part of the lens. And when light passes through one of these lenses, the light gets focused into one point. A magnifying glass is a good example of that. The other type is called a diverging lens, or sometimes a concave lens, because the middle is thinner than the outside. Light does not get focused by this, but rather light gets spread out by this type of lens. Here's an example of a light traveling through a concave lens. Over here on the left, we have a box that has little openings in it and a light bulb on the inside. And so these openings, light travels through these openings. It gets refracted by this lens, and notice that the rays begin to spread out. This is a diverging or a concave lens. Makes the light spread out. Let's try this picture instead. We'll come back to that in a moment. Whoops. A convex lens, on the other hand, light coming out of that light box. It's just a box with little openings in it, nothing fancy about it, and a light bulb. Light comes in, so we can see these little light beams coming in. Notice that the light coming right through the center of the lens goes just about straight, and the light that is coming from the edges gets bent or refracted into a point. over here that we call a focus point. So this type of lens focuses light. For Snell's law in reflection, we have this mirror that's curved, and the shape is actually a parabola. It's a parabolic shape. Yes, the same mathematical parabola that you study in algebra. This is the shape of the lens of a telescope. Angle of incidence equals angle of reflection. So if a beam of light is traveling right down the middle of this, light will get reflected back up, straight back up. For a light beam coming out near the edge of the mirror, angle of incidence equals angle of reflection. So if I draw the normal line in there and the normal line on top, we can see that the angles are equal. And so the light then gets pushed out here into this spot. That is a focus point. In telescopes, we sometimes call that the prime focus. So this is a type of mirror. Most reflecting telescopes have large mirrors in them that use the basics of Snell's law of angle of reflection equals angle of incidence, so that the light gets focused into a point. And the mathematical shape of that mirror, of course, it's three-dimensional, but it's when we cut it in half and look into it, we have a parabola, a parabolic shape. We also have concave lenses. Convex lenses. Some of these convex lenses mirrors are in telescopes. But in this case, these mirrors make things look smaller. And you have some examples of these kinds of mirrors. Here's, for example, a convex mirror that you sometimes will see in a store. This gives the owner, the employees of the store, the ability to see across wide areas. This happens to be at a dangerous intersection where a driver can see around the corner. Sometimes you'll see these on the school buses so that you can see a large area. Sometimes on cars, they allow the driver to see into the blind spot. They make things look smaller, but you can see a large area with them. Concave mirror. A good example of a concave mirror is a bathroom mirror. It magnifies when you look into it. A good example of a mirror that has a curved shape like a telescope mirror. One application, very briefly, that's really not what we're talking about in the class, but is interesting for energy purposes, and this is a solar cooker. We happen to have a parabolic mirror, concave mirror, and have up here at right where the prime focus is, right where the focal point is, for example, a cup of coffee. And putting this mirror out in the sunlight, aiming it at the sun, all of the light will come in and get concentrated at this point and can cook that warm heat and perhaps even boil on a real sunny day. And if the mirror is pointed directly at the sun, can actually boil that water that is in that cup of coffee. So that is a practical application. And for bigger areas in some of the solar energy projects, we have big mirrors that are collecting lots of light and boiling water that runs the steam turbines in the solar electric plants. So this is a basics of Snell's law, basics of reflection by curving the surface. Here then are examples which we'll get to next time are the refracting telescope and the reflecting telescope. Reflecting telescope uses a lens that is convex. A reflecting telescope uses a mirror that is concave. We actually look into the eyepieces of these, which creates the image that we see. These are the basics of reflection and refraction based upon the principle of Snell's law so that when light goes from one medium, air, to another medium, glass, or air to water, certain things occur with that light. Either the angle is equal for reflection, or the angle is bent or refracted when it goes into the medium. Angle of incidence equals angle of reflection. And Snell's law for refraction is that when light goes from air into glass, it gets refracted toward the normal. Its angle gets smaller.